This section is on hydrogen ions and pH. This is going to be a pretty important section for our next test. There's going to be several important equations. It's going to talk about how we calculate pH, which you may have heard of before, and sort of what the range of pH is, why it is what it is, and how we calculate it. So, going back to pure water, in the last video we saw the equation to see what happens when water dissociates with itself. It forms hydronium ions and hydroxide ions. And in pure water, this happens just a tiny bit. I told you it was about 1 in a million water molecules at any given time will do this. And when it comes apart in pure water, the hydrogen ions and hydronium ions come out equal. And that's about 1 times 10 to the negative 7th molar. That's just what it is, actually. It's a very, very tiny, tiny number. But there's an important equation that comes from this. And it's this one right here. And you're going to see 6 equations today that you definitely want to get into your notes. So here's the first of them. And that is if we take this hydrogen ion concentration of pure water and multiply it times the hydroxide concentration of pure water, we get this 1 times 10 to the negative 14th. So if we take 1 times 10 to the negative 7th times 1 times 10 to the negative 7th, you add those exponents together. Negative 7 plus negative 7 is negative 14. Okay, and so this is the first equation here. But this is also true for acids and bases. And let's say I do something that makes the solution more acidic and increase the hydrogen ion concentration, or hydronium. Don't forget, H+, we're going to consider the same thing as H3O+. Okay? If I increase the hydronium ion concentration, in order for this number to be constant, which it is, this concentration must go down. Okay, so if this one goes up, this one must go down, and then the opposite's also going to be true. If I increase the hydroxide ion concentration, my hydronium concentration is going to have to go down, because together, in all cases, these two things multiplied together equal 1 times 10 to the negative 14th. This equation has a name. It's called the ion product constant of water. Ion because, well, these are the ions. Product because we are multiplying, and constant because it always equals this value 1 times 10 to the negative 14th. So this is our first important equation when it comes to solving pH problems. Okay, so because these numbers are very small, right, in pure water it was 1 times 10 to the negative 7th molar, chemists have adopted an easier way to write and record values, and that's using pH. And the equation for pH, and this is important equation number 2, pH is equal to the negative log of the hydrogen ion concentration. You will also see this written as pH equals negative log of the hydronium concentration, right? Because don't forget, we are considering H plus to mean the same thing as H3O plus, okay? But that's the equation. pH is negative log of the hydrogen ion concentration. And you should have done logarithms in Algebra 1. And we'll cover how you plug this into your calculator here in a few minutes. The temptation is to say pH equals negative log times the hydrogen ion concentration. That's not how you read this. You say pH equals negative log of the hydrogen ion concentration. So that's important equation number 2. To reverse this, to go backwards, the hydrogen ion concentration is 10 to the negative pH. So that's up there as an exponent, 10 raised to the negative pH. So this is the reverse of this equation. So this is equation number 3. Okay. So checking this, the hydrogen ion concentration in pure water, which we saw on the previous slide here, was 1 times 10 to the negative 7th molar. What is the pH? So what you want to do, and check this with your calculator now to make sure that you are getting the correct value. We're going to type in the negative sign. You'll hit the log key, and it'll put a parenthesis there for you. And what you want to plug into your calculator is 1, the E function, negative 7, close your parenthesis, and it should spit back to you 7. Okay? So remember, that's the E function. How you get to that is the second button and then the comma button. It gives you that E function there. So that's how you type that in. So you should get 7. And if you know anything about pH, you should know that 7 is the neutral point, that it's not acidic or basic, that it is right in the middle there. And that should work out. Right? If the concentration here is 1 times 10 to the negative 7th, my pH should be 7. The pH scale is based on powers of 10. And this is usually one of the more confusing things for students to pick up on at first. A pH of 3 is 10 times more concentrated in terms of acidic. It's 10 times more acidic, we should say, than a pH of 4. Okay, it's not, 1 times more concentrated. That doesn't make sense, even though they're, 1 unit apart. They're 10 times more concentrated, and each number you move down is 10 times more concentrated. So, for instance, then, a pH that is 2.0 is 100 times more concentrated than a pH of 4. And a pH equaling 1 is 1,000 times more concentrated than a pH of 4 in terms of how acidic it is. Okay, so it's really 10 raised to the difference of those two in terms of how much more concentrated it is. You need to think of it like that. This will make a kind of a good, short, multiple choice question on the next test, maybe. Okay, we can also do the same thing for hydroxide, but instead of pH, we call this POH, which stands for power of hydroxide. pH is power of hydrogen. And that equation is negative log of the hydroxide ion concentration. So you type in your calculator negative log of whatever this number is, close your parentheses. Okay, that would give you POH. And then similarly to the last slide about the hydrogen ion concentration, you can also find the hydroxide concentration by taking 10 to the negative POH. Okay, so that's important equation number 5. And the last one here, important equation number 6, pH plus POH equals 14. Okay, so those are the 6 equations you definitely want in your notes. Now, as far as how we calculate some of this stuff, over here is a pH chart. Remember, 7 is the neutral point. Things this direction are basic. Things this direction are acidic. So you can kind of see some examples here. Battery acid, very acidic, not really stuff you want to get on you. Stomach acid, pretty acidic. Lemon juice, very similar. Soft drinks have a pH of about 3, so Coke's pretty acidic. Vinegar is down there. Tomatoes are acidic. Coffee is acidic. Milk is slightly acidic. The other direction, blood, slightly basic. Seawater, antacids. Detergent, milk of magnesia. It's a laxative there. Household ammonia. And oven cleaner, very, very basic. So is drain cleaner. Really, really basic stuff. So, how do we calculate some of these things? The household ammonia has a pH of about 11.6. What's the hydroxide ion concentration? So what we would do is, okay, this is the information given to us, has a pH of 11.6. And we look for equations that could get us to this number right here. Well, first of all, using equation number 6, which is pH plus POH equals 14, okay, I can get then that POH is 14 minus pH, which is 14 minus 11.6, which is going to be 2.4. So my pH is, or sorry, my POH is 2.4. Oops. And then from that, if I use this equation, 10 to the negative POH, I can get my hydroxide ion concentration. Okay, so that's from equation 5. Hydroxide concentration is 10 to the negative POH. So it's going to be 10 to the negative 2.4. Okay, so on your calculator, 10 caret negative 2.4, that's going to give us 0.00398 molar would be our answer here. Okay, and that's how we could figure that out using the equations that we've learned. Here we see a pH chart. It's a really good summary, kind of showing you how things change with pH. Our neutral point here is at pH of 7. And if you remember from a few minutes ago, the first equation we learned was that the hydrogen ion concentration times the hydroxide ion concentration is equal to 1 times 10 to the negative 14th. And here, at a pH of 7, the hydrogen is 10 to the negative 7th. The hydroxide is 10 to the negative 7th. Those two multiply together give us that value. We'll go kind of left here and then talk about what happens when we go right. If I go to a pH of 6, that means my hydrogen ion concentration is 10 to the negative 6th, and that my hydroxide concentration is 10 to the negative 8th. Note that it doesn't mean that hydroxide goes away as we become more acidic. It just means that there's less and less and less of it as we go this way, and more hydrogen ions. This is going to be 10 times more acidic, okay, at a pH of 6 than a pH of 7. A pH of 5 is going to be 100 times more acidic than a pH of 7. A pH of 4 is 1,000 times more acidic. 3 would be 10,000 times more acidic. 2 would be 100,000 times more acidic. A pH of 1 is, 1 million times more acidic. Okay, so I think you're getting the idea here. A pH of 0, I think I did everything right there, is 10 million times more acidic than a pH of 7. Okay, so I think you guys are starting to understand, hopefully, how this works by looking at that. And if I go the other way, becoming more basic, okay, notice my pH is going up. pH of 8 means I have a pOH of 6, since, if you recall as well, pH plus pOH is equal to 14. So if I have a pH of 8, I've got a pOH of 6. My hydrogen ion concentration is going down significantly, right? 10 times for each number here on my scale. And my hydroxide ion concentration is going up 10 times for each one. So this pH of 8 is 10 times more basic than a pH of 7. A pH of 9 is 100 times more basic. A pH of 10 is 1,000 times more basic. pH of 11 is 10,000 times more basic. 12 is 100,000, right? 13 is 1,000,000. And a pH of 14 is 10 million times more basic than a pH of 7. Okay? Notice again that as we go this direction, my hydroxide is going closer and closer to a concentration. Here it's 1 molar. Okay? But my hydrogen ion concentration doesn't go away. It's not that it doesn't exist. It's just significantly tinier. Okay? So anyways, that's how this scale works. Numbers change pretty slowly at the extremes of the scale, and then in here in the middle, changing from pHs of 6 to 8, if you add a little bit of acid to something that's a pH of 8, or a little bit of base to something that's a pH of 6, this changes very quickly here in the middle, which we'll see in our next section. Okay, go ahead and pause the screen here and copy this down before you start listening to it. Okay, this is the pH square. Essentially what we are doing, we are taking those 6 equations, those super important equations that we saw earlier, and what I've done is conveniently put it into a format that allows you to just simply find your point on the pH square and move yourself around to solve for whatever you need using the 6 equations. So they've already been solved for the variable that you need. So if you're given pH, you can find the hydroxide concentration. If you're given hydronium, you can find the pH. If you're given pOH, you can find the hydrogen or hydronium ion concentration. Thing to remember here is that H plus is really the same thing as H3O plus. So you could put H plus in this thing's place. Both of those are the same right there as well. Okay. And we're going to use this to solve pH problems. So if you want to know, like, what's the concentration of certain things, what's the pH of it, we can use this box here, the pH squared, to solve that. Okay, so here's an example problem, and then we'll do one off of the worksheet together. It says 2 grams of NaOH is put in 400 milliliters of solution. What is the pH of the solution? Okay. Now, if you notice, looking at that pH square that you just wrote down, there is no spot for moles. The only way that you can put something into the pH square is if it's already giving you a pH or pOH, or if you have a concentration. All right. Here, we got to work our way to getting to this point, and then we can enter the pH square. So my plan of attack is taking my grams that I started with, converting that to moles. So that's going to be dividing by molar mass. And then turning that into molarity, which is moles over liters. So I'm going to be dividing by liters to convert that into molarity. And then here, okay, we can enter the pH square. Okay, and we can actually enter it. We'll have to enter it at the point where of the hydroxide ion concentration is. But how we move around the square, we can go in any direction. We'll get to the correct answer. So we'll have the hydroxide concentration. We can solve for pOH and then pH. So how we solve this? So let's go ahead and do this. I'm starting with 2.00 grams of NaOH. All right. I need to get moles of that. So just simply dividing by molar mass. NaOH is an easy one to remember because it's 40.00. Okay. And that's going to give us, let's see, 2 divided by 40 to 3 significant figures, 0.0500 moles of NaOH. All right. And then if we want to get a concentration of this, we're going to take the second step here. Will be divide by liters. So we've got 0.0500 moles divided by, remember this has got to be in liters, not milliliters, so divided by 0.4. And that's going to be a molarity of 0.125 molar. Now, you could say this is the sodium hydroxide concentration, but if you remember from the previous video, when you put sodium hydroxide into water, it breaks apart completely into sodium ions and hydroxide ions. So really, this is also the sodium ion concentration or the hydroxide concentration. And so what we're going to do, instead of considering it as the sodium hydroxide concentration, we're just going to call this 0.125 molar is also the hydroxide concentration. And that's because this thing's a base. So when it comes apart, it's a strong base, so it comes apart completely. So we can say that those two things are the same here. Well, now I have a piece of my pH square. I've got the hydroxide ion concentration. I've got the bottom left part of the square. And it wants me to move towards pH, right? The answer wants a pH. So I can do two things, okay, in terms of my square. Remember, my hydroxide's down here, my hydrogen ions are here, my pH is here, my pOH is here. I could go two ways. I could go up and then over following the arrows. I do whatever mathematical expression the arrows tell me to do, or I can go to the right and go up. Okay, it's probably going to be easier to go this way. Okay, so what we're going to do is follow along with the arrows that tell us how to get to that. So going from the hydroxide ion concentration here to pOH, okay, is negative log of the hydroxide ion concentration. So we're simply going to find pOH by doing the negative log of this, right, the number we just found. So that is 0.125. And when you type this in your calculator, you push the negative sign, then the log key, and then 0.125. And we get 0.903. Okay, and that takes us to this point on the pH square. And then to get to pH, right, that is going to be 14 minus pOH. And if we do that, 14 minus 0.903, it's going to give us 13.097. So that would be our final answer here. And just a couple of like mental checks that you can do. First of all, if it's a pH or a POH as a final answer, my answer should be between 0 and 14. So we can ask ourselves, is our answer between 0 and 14? Yes. Also, we know that this is a base, don't we? An AOH is a strong base, and I'm putting that into water. So I should expect my pH to be between 7 and 14. Well, I get 13.97, and so that also checks out. If I had done this and my answer was less than 7, that means I probably solved for the pH, or yeah, the POH instead. Okay, so we get an answer between 7 and 14 because that's where the basic scale is for pH. So both of those answers check out. This answer makes sense. And this is a strong base, and we're putting it in not a whole lot of water, so we should expect a very high pH out of that. So there's our first sample problem. Now we'll look off one from the homework. Okay, so this is from problem 1. It says if 0.500 grams of lithium hydroxide are dissolved in 0.750 liters of water, what is the pH of the solution? Okay. So I went ahead and wrote down the numbers on here. Let's think about our plan. It's going to be very similar to the one that we just did. I need to, in order to get into the pH square, okay, I need a concentration. I need something in molarity, right? Okay, so I'm not given any of that. I need to first work for that. Then I can enter the pH square, and I simply just follow whatever mathematical expressions take me to my final answer. I've got 0.500 grams of lithium hydroxide. The one that's information that's not given to you in the problem and that you will need is the molar mass is 23.95 grams. So our first step is to get this into moles. Step 2 is convert moles into from grams to moles, then moles into molarity. This is a base, okay? So my molarity there is a hydroxide ion concentration. So if I really want to be even more specific, right, really what I'm finding here is the hydroxide ion concentration. Since this is a hydroxide, acids, you'd have the hydrogen ion concentration. All right, and then from that, I can find POH, and then from POH I can find pH, which is what the question was asking about. So step 1, to find moles, my grams to moles, it's going to be divided by molar mass. So I've got 0.500 grams of LiOH divided by 23.95 grams per mole. So my first number here is, let's see, 0.5 divided by 23.95. This is 0.0209 moles of, we could say lithium hydroxide, or since it comes apart completely, we're just going to say hydroxide ions. Step 2 is to get it into a concentration, so we're going to divide by liters. It gave us a number in liters, so we don't have to do any conversions here. My hydroxide concentration is simply going to be 0.0209 moles divided by 0.750 liters, moles divided by liters. So that number divided by 0.75 to 3 significant figures, 0.0278 molar is my hydroxide concentration. And then from there, I can enter the pH square. Okay, and once again, I'll kind of shorthand draw this. All right, that's what's on that side. POH is there, pH is there, and the hydrogen ion concentration is here. I could do this 2 ways. I could go up and then over, or I could go this way and then up. The easier route's probably this one, but I can prove to you that this one gets you the same answer, so we can solve this really in 2 ways. To get to the hydrogen ion concentration, so I'm going to go up and then go to the right. It was 1 times 10 to the negative 14th divided by my hydroxide concentration gives me the hydrogen concentration. So let's do that one first. So it's going to be hydrogen ion concentration is equal to 1 times 10 to the negative 14th divided by, and my number here is 0.0278. Okay, Let's see what that gets us. So 1 times 10 to the negative 14th divided by 0.0278. And this is 3.60 times 10 to the negative 13th. And then to go from hydrogen ion concentration to pH, it's negative log of the hydrogen ion concentration, or H3O plus, either way. So negative log of that number, negative log of 3.60 times 10 to the negative 13th. Okay, so if we plug that in, we get 12.44 is the pH. Okay, so that was going up and to the right. Let's show you what happens if we go to the right and then up and see if we get the same result. Okay, so this side here was the first version of it, right? And we'll do the other one on this side. So if I go this way, if you follow the arrows, you just do whatever mathematical expressions pointing in that direction. This is going to be negative log of the hydroxide concentration. So POH is negative log of the number that we got right here, which is 0.0278. So negative log of 0.0278 is 1.56. And then the POH to pH is simply 14 minus POH. So 14 minus 1.56 should be 12.44. Okay, so it doesn't matter which way you go, you will get the same result.